So we are now on lesson 6, motion in two-dimension projectile motion, part 3 of the lecture video series. So for video presentation, we're going to have 2 more additional practice problems that you can work on your own. Let us start. So for our first problem set, we have here a metal ball. Let's read that one. A metal ball which is launched horizontally off a cliff that is 19 meters high. It is launched with a speed of 11 meters per second. First question is how long is the projectile in the air, and how far from the base of the cliff does it land, and what is its final speed? Okay. So just like our previous examples, first step that we need to do is to illustrate it. So we can visualize what we're talking about here. Okay, so this is the cliff. And this is the ball. Okay, so it's launched at a horizontal motion, something like this. And of course, it will eventually move in a projectile manner because of gravity. Okay, and let's write down our given. First, we have here a 19 meter high, and it's launched with a speed of 11 meters per second. Okay, so this is 19 meters. And its initial velocity on the x-axis is 11 meters per second. So one thing to note here is that this one, again, remember that it is launched horizontally, meaning all of these 11 meters per second are directed to the x-axis. Okay, so we also have our gravity, that would be negative g, which is negative 9.8 meters per second squared. Okay, so for our first part here, our question is how long is the projectile in the air? So that is the concept we have done last time, which is time in the air. So that's our first question. Now, what formula are we to use? Let's analyze. First, figure out what dimension are you trying to work on. And since we are here, time in the air, which means once it is released here from the top, how much time would it take for it to fall on the ground? Okay, so that's in y dimension. If you are to look at this one here, our formula, let's look at our first formula here. We're searching for t. We have g. Let's check that out. We have g. We have initial. And what we don't have, final velocity. Okay, for the second one, we're searching for time. So that's present there. And we have our initial velocity. We have our initial position, and of course, we're going to have our final position. So between first and second equation, the most appropriate one would be the second equation. The third one, of course, obviously we can't use this because there's no time indicated in that formula. So let's write it here. Write yf is equal to yi plus viy t plus 1/2 gt squared. Okay. Next step, try to analyze if there are parts of this equation that we can equate to 0. Y final would be 0. Y initial won't be 0, obviously, because we started at 19 meters. So that would be 19 meters. VIY is our initial velocity on the y-axis. Again, kindly remember, VIY is the initial velocity on the y-axis. And since our story here, we launch it horizontally, what will happen is that our VIY here would be 0, making this 0. So we're left with the formula 0 is equal to, let me change that ink to blue. We're left with 0 is equal to yi plus 1/2 g t squared. We want to isolate t. Kindly remember that you want to isolate t. Okay, what I want to do now is to transfer yi, this initial position, into the other side of the equation, making it a negative yi is equal to 1/2 gt squared. Okay, so isolating let's write down our, I think we can already write down our units or our variables. Yi is our initial position, and that's 19 meters. Write it here, 19 is equal to 1/2, that's 1/2 negative 9.8, so this should be negative 19 t squared. Okay, simplifying, sorry, put it here. So simplifying this, we're going to have negative 19 is equal to negative 4 get my calculator so I can compute already. Okay, here's my calculator, and of course this is 1/2 multiplied by negative 9.8. That'll be negative 4.9 t squared. Okay, so we have to divide both sides by negative 4.9. So we can isolate t squared there. Cancel. And our formula would be t squared, ililipat ko lang, is equal to negative 19 over negative 4.9. This is t squared, so we want it to be t only, so we can get a time. So to do that, we have to remove the square here by square root, by putting a square root on both sides. Cancel, cancel. Our final formula, our final answer is t is equal to, get your calculator, let's compute for that, negative 19, negative 4.9. Okay, our final answer is 1.969. So for 2 decimal, that's 1.97 seconds. Okay, so that's our time in the air. Any questions? Let's now proceed with our second question, our letter B question. This is letter B. How far from the base of the cliff does it land? Okay, for letter B, we are asked to how far from the base of the cliff. And that is a concept of range, which means that if this is the start of the base here, gaano kalayo itong part na to? That's the how far from the base of the cliff will it land. And that is the concept of x dimension. Okay, so if that is the concept of x dimension, we are actually searching for xf. And xf would be, obviously, here is the second formula. So let's transfer it here without any hassle. Xi plus Vixt plus 1/2 AT squared. Okay, so that's our formula. Next is to find out if there are parts of the formula there that we can equate to 0. Final position obviously won't be 0. Initial position, this is the part there, that's xi, should be 0. Because if you are to convert this into a coordinate system, that would be 0. Vix is the initial velocity on the x-axis, and that won't be 0. A, or acceleration in terms of the x-axis, is 0 primarily because it's launched at a velocity of 11 meters per second and there's no other factors affecting that, unlike gravity. Remember that gravity only affects the y dimension. So this A should be 0. Our final formula would be xf is equal to Vix t. Okay, so I think we can already compute for this. Our Vix is of course 11 meters. So that's 11 multiplied by time, which it took for that situation to happen, and we have searched that as 1.97. So we'll just multiply that, 1.97. Let me get my calculator. You can also compute on your own. Okay, so that's 21.67. 21.67. We are searching for final position, and position is in meters. So our XF here is 21.67 meters for question letter B. Okay, last one. For letter C, our question is the final speed. So the final speed is in terms of the Pythagorean theorem, right? So for example, if this ball started here, and we imagine that this is the final position before it lands, magkakaroon siya ng what we call here the final velocity. Okay? And that should be at a projectile, which means that this should have Vfx, which is the final velocity before it lands on the x-axis, and Vfy, which is the final velocity on the y-axis before it lands. Okay, so obviously we have Vfx that is 11 meters per second. So our Vfx, we don't have to search for it, that's already 11 meters per second. The question now is our Vfy. Why do we need to search for a Vfx and Vfy? Because we are searching for the resultant velocity, which means at the end, to search for the final velocity or the final speed, our formula would be the square root of Vfx squared plus Vfy squared. Okay, so let's now try to search for our Vfy. We obviously would have to look at our formula here at the top. And we actually have a formula searching directly for Vfy. That is the first formula here. And so we write it down because obviously that's what we're going to use. So Vfy is equal to Viy plus gt. Okay, so what is our initial velocity on the y-axis? According to our story here, we started at a velocity at a horizontal velocity of 11 meters per second. However, there's no velocity given on the y-axis, which means that our initial velocity here in the y-axis is actually 0 meters per second, which allows us to cancel this one, which means our final velocity would be negative 9.8. It's the time. That's the gravity multiplied by the time for this situation to happen, and that's 1.97. Okay, so let me get our calculator. The answer is 19.31. Negative 19.31 meters per second. So that is now our final velocity here, negative 19.31 meters per second. And we now have a value for a VFX and VFY. So let me put it here. Let's try to compute that. Square root of 11 squared plus 19.31 squared. Okay, pwede na natin hindi lagay yung negative since squared naman siya. The answer for that is 22.22. 22.22 meters per second. And that is now your final velocity for this situation. Any questions? Okay, we'll now proceed with our final example problem. For this one, our question goes like this. There's a penny here. There's a penny which is thrown off a bridge with a height of 75 meters at an angle of 25 degrees with respect to the horizontal. If the initial velocity of the penny is 15 meters per second, our question would be, what is the maximum height and what is the time in the air? Okay, first, let's illustrate that. And here's our bridge. I think I'll draw the bridge here at the side. Here's our bridge, something like this. And here's our penny, which is thrown at an angle of 25 degrees, and of course it will move at a projectile, something like this. Okay. Highlight our givens. The height of the bridge is 75 meters. The pen is thrown at about 25 degrees with respect to the horizontal. If the initial velocity is 15 meters per second, we search for the following quantities. Okay, let's write it here. First, this bridge has a height. Let me use a red ink. Has a height of 75 meters. And this penny is thrown at an initial velocity of 15 meters per second at an angle of 25 degrees. So those are our given. Okay, so first question is, what is the maximum height? And height is dimension in terms of the y. Okay, so y, a dimension. And maximum height is actually y max. Okay, so what is our y max? Our y max is simply the height added between the 75 meters plus kung gaano ito yung inangat niya here and the 75 meters. Okay, so this one is the height which should be added, and this height here. And all throughout, yung isang buo na yan, that's our y max. So that's what we're trying to search, the y max. Let me erase this one, Okay, how do we do that? Okay, looking at this one, it's obvious that we are to use the second formula for the YF or the Y final which is the Y max of course. However, according to our story here, we're not yet given the time. Okay, so we have to search for time before we try to solve for YF. I think we have already done an example problem like that. And for the formula that we have to use in searching for time would be the first one, obviously, because we cannot use a third one, and the second one, the second formula here has a lot of missing. So let's write down here our formula in searching for time in the air. We'll search first for the time in the air, and that would give us VFY is equal to VIY plus GT. Okay, again, remember that you want to isolate GT. Find parts of the equation that we can equate to 0. Okay, first, our final velocity would be 0. Okay, so why would it be 0? Again, when you throw something, eventually it will come to a halt, and then before it goes down. Our initial velocity on the y-axis would be, again, remember that this VI here, let me draw it one. Our VI here is the resultant, which is 15 meters a second. And it is composed of accompanying VIX and VIY. And for that, we go to SOHCAHTOA, and I won't dwell any further with that because we have already done that. VIY is, if this is your angle, it's on the opposite side, so that would be VI sine theta. Meanwhile, VIX will be VI in cosine theta. Okay, which means that our VI here would be VI sine theta plus GT. Okay, so our VI is obviously 15 meters, so this would be 15 sine the angle, which is 25 degrees. Plus negative 9.8. And then we're searching for time. Okay, so let's continue here. 15 sine 25 degrees. Let me compute that. Sine 25 is 6.339. That's 6.34. 0, 0, 0, 6.34 plus minus is negative 9.8t. Okay, I'll transfer 6.34 on the other side, making it negative, or pwede rin yung negative 9.8, bahala kayo. But for now, I'll transfer 6.34. Okay, 6.34 is equal to negative 9.8t. Divide both sides by negative 9.8. Cancel, cancel. Our final formula now for the time in the air, the answer rather, for time in the air is, get your calculators, negative 6.34, negative 9.8. That's 0.646. So that's 0.65. Okay, 0.65 seconds. So that is now our time in the air. This is actually the second question, which means we have already answered our second question. Okay. So according to our discarte a while ago, we used the second formula to search for the maximum height. So let me change this, sorry, to maximum height. Okay? Pinagbaliktad lang natin yung question. So the formula for that would be YF is equal to YI plus VIYT plus 1/2 GT squared. Okay. Again, we want to search for the YF here. Let's find out if there are parts here that we can cancel out. YF won't be 0 because that's what we're trying to search. YF is equal also Y max. YI would be the initial position of the penny before it reaches the Y max. And that's actually 75 meters. Again, let me reiterate. The YI here would be the part whereas before the initial position of the penny before it reaches the maximum height or YF. And that is actually 75, which is 75 meters, the height of the bridge. Plus the initial velocity on the y-axis. Again, initial velocity on the y-axis. So that's VI sine theta, which is 15 sine 25 degrees multiplied by time. And our time is actually 0.65. Plus 1/2 negative 9.8. Ayusin ko yan. Negative 9.8 multiplied by 0.65 is squared. Okay. We can actually plug this in our calculator already. So let me get my calculator. Kindly get your calculator also. 75 plus 15 sine 25 multiplied by 0.65 plus 1/2 negative 9.8 0.65 squared. Okay, the answer is 77.05. 77.05 meters because we are searching for the YF or the Y max. This is the answer here. Okay, so that's it. That's how you search for the time in the air and the maximum height at a problem like this. On our next question, we are to continue with the same question. But this time we're going to search for the range and the time at which the rock lands and the velocity of the rock. Okay, next slide. We are trying to search for the range. So the range is actually our XF, if you can recall. Let us draw again our illustration here, which is the bridge. This is the ground, this is the penny, launch, and move at a projectile. Its velocity here is 15 meters per second at an angle of 25 degrees. Again, same question as same story as kanina. And this is 75 meters. Okay, we're searching for XF. For short, we're using the X dimension as our dimension. And obviously, XF is this formula. Okay, so for the XF, let's write down here our formula. XF is equal to XI plus VIXT plus 1/2 AT squared. Okay, let's look at if there are parts of the formula that we can equate to 0. XF won't be 0, obviously. XI would be 0 primarily because if this is our XF, which is the final position, it will start here. And in terms of the coordinate system, that should be 0. Okay. VIX won't be 0 because we have here an initial velocity at an angle, which means just like the VIY, we have our VIX. And the formula for VIX is actually VI cosine theta. Our T, or the time in the air, we have already actually solved for that a while ago. And in terms of our acceleration, we are now looking at the X dimension. Gravity won't affect it. So our acceleration would be 0, canceling this part. So we are left with XF is equal to VIXT. Okay, what is our VIX? That is VI cosine theta multiplied by the time. For that to happen, okay, so this time, our time here won't be the time on example A and B. Why? Because last time, if you can recall, what we have done is we just searched for the time for the object to reach its time at the maximum. This time, we are searching for the time it took the ball or the penny from here, from this position, up to this position. And for us to do that, we are to use the obvious one, which is yung lagi natin ginagamit, the second y formula here. So let's write it here and then we'll plug it there. So that's yf is equal to yi plus viyt plus 1/2 gt squared. Finding out if there are parts here that we can equate to 0. Our final position in terms of the whole story here, this is 0. Our yi won't be 0. Our initial position is this one, right? Which is 75. Plus vi. Our vi is our initial velocity on the y-axis. So that's 15 sine 25. Multiplied by time. And we don't have time yet that it took for everything there to happen. Plus 1/2 g is negative 9.8 times squared. Okay, let's simplify this one. So that will give us 0.75 plus, let's compute 15 and sine 25. 6.339, so that's 6.34. 6.34. 6.34 t plus minus, that would be negative 4.9 t squared. Okay, I hope you can recall. This is the part of the quadratic equation we have done on our previous example. Okay, so if we are to use the quadratic equation, what will happen is that we're trying to search for t here. Plug that in a quadratic equation. I won't discuss it anymore here. Kindly go back to our first example last time. But just remember the quadratic equation and plug here your ABC. So this would be your A, this would be your B, and this would be your C. Your R, you want to isolate T. If you are to compute that, your final answer would be 4.61 seconds. So this is now the time it took the penny to go from here up to the end. We'll plug it here. 4.61. Sorry. Let's make this t. And we plug in our value. Our VI is 15 cosine 25 multiplied by time, which is 4.61. Okay. Put that in your calculator. That's 62.67. 62.67 meters. Okay, so our range is 62.67 meters, which means when the penny is launched here from this position here, it will reach a range of 62.67 meters. So ganun kalayo. Okay. Next question is the velocity of the of the penny just before it lands. And we have already done an example like that on the previous example. So that's Vf is equal to the square root of Vix squared plus VIY squared. Okay, do we have our VIX? Have we searched for it a while ago? That's 15 cosine 25, right? Let's check. So our VIX on the x dimension here, that would be this formula. Let's write it here. VF, sorry, this should be VFX and VFY. So our VFX is equal to the VIX plus AT. And since again we are talking about the acceleration in the x dimension, there's no acceleration in the x dimension, we can cancel this one, which means our VFX is actually equal to our VIX. What is our VIX? Our VIX, according to our definition a while ago, is actually VFX is equal to VI cosine theta. And our VI is 15 sine 25. Sorry, cosine 25 degrees. Okay, so that's our value of our VFX. How about at VFY? Our VFY, according to this equation here in our y dimension, the formula we are to use is this one, right? So let's write it down. VFY is equal to VIY plus GT. Our VIY is the initial velocity on the y-axis, so that's VI sine theta plus GT. Do we have our G? Yes, and we have also our time in the air, or the time it took to land, so that's 4.61. Our VI is 15 sine 25 degrees plus negative 9.8 multiplied by the time the penny took from the bridge to the ground, that is 4.61. Okay, let's compute for both para madali na lang ilalagay natin dito. $15 cosine 25 is 13.59. So that's 13.59 meters per second kasi nga we're searching for final velocity. Meanwhile, on the y-axis, that's 15 sine 25. Negative 9.8 multiplied by 4.61. That's negative 38.83. So that's negative 38.84. Negative 38.84 meters per second. Okay, so that's our value of VF here and VF. And VFX here and VFY, let's plug it here. That's 13.59 meters per second. So, sorry, let's not write here. Squared plus 38.84 squared. Okay, our final answer is, let me erase this part here. Okay, our final answer would be the square root of 13.59 squared plus 38.84 squared. 41.148, so that's 41.15. 41.15 meters per second. So this is now our final velocity, meaning the penny before it lands, ganito yung bilis niya. Now the direction is actually the TOA in SOHCAHTOA. Okay? And that would be the angle is equal to arctan of our opposite and adjacent. So let's write here. Let's draw again our VI. Our VI is 15 meters per second. And if we are searching for the angle here, Okay, this is our VIY and then this is our VIX. If we are searching for the angle, our VIY would be the opposite. So in TOA, that's opposite over adjacent, you're searching for the angle. So our opposite would be VIY. So we'd put it here, VIY. And our adjacent is VIX. So let's write it here, VIX. Okay, so let's plug that in our calculator. Arctan, VIY is negative 38.84. Our VIX is 13.59. Okay, I'm sorry, why did I put a negative sign there? That should be positive. Anyways, kindly compute shift tan for arctan. So that's negative 38.84 over 13.59. So the angle is actually negative 70.7. That's negative 71 degrees. Okay, so this is now the direction of our velocity, which is 41.15 meters per second. Okay, any questions? This arctan here, this one, it's in your trigo, which is the TOA in the SOHCAHTOA. If you don't want to recall that, just remember that arctan here, shift in your calculator, that's shift and then tan. Okay, is equal to opposite over adjacent. So this is our opposite. You just have to find out if this is your angle, what is the opposite and what is the adjacent. That's why VIY and VIX. Sorry, that should be VF, not VI. VF. Okay, so that's it. That's how you do it. Again, any questions? Thank you so much for listening. That is the end of our projectile motion examples.